Good morning. Welcome to manufacturing process lecture classes. Today we are going to start a new module, module number 9 on non-traditional manufacturing. Today we are going to cover broadly two areas of non-traditional manufacturing. We are going to introduce the subject of non-traditional manufacturing, and after that we are going to take one manufacturing process within it, which is abrasive jet machining. Before going into the actual lecture, let us identify the instructional objectives. What are instructional objectives? This basically says what we are going to learn today. Today we are going to mainly identify the characteristics of different conventional machining process. Our lesson is on non-traditional machining process. So, first we need to know what are the characteristics of the other machining process, namely conventional one. Once we have learned that, we are going to come to the characteristics of non-traditional machining, general characteristics. Once these two have been achieved, then we can differentiate between the conventional machining processes as well as non-traditional machining processes. Then there are different types of non-traditional machining processes. So, we need to understand classification of non-traditional machining processes as well. However, conventional machining processes were there for ages and they were serving all the purpose. So, why all of a sudden there was a need for non-traditional machining processes? That also is required to be studied. So, these 1, 2, 3, 4 and 5 points basically deals with the introduction part. The other instructional objectives, namely are on abrasive jet machining processes. First one is we need to understand the basic mechanism of material removal of abrasive jet machining. We need to understand the major components of abrasive jet machining equipments, their working principle. We should be able to draw the AJM equipment or abrasive jet machining equipment once you go through this particular lecture. We need to understand what are the process parameters of abrasive jet machining and what are the machining characteristics, and analyze the effect of process parameters on one such machining characteristics, which is material removal rate. Draw variation in material removal rate, which is the primary machining characteristics, with different process parameters. That means, if we can do that, we would be able to understand what is the effect of one process parameter on one of the most important machining characteristics, namely material removal rate. We are also going to develop mathematical models relating material removal rate with respect to AJM parameters. Last but not the least, we need to understand the application areas of AJM and limitations of AJM. So, first we will start with the basic classification of manufacturing processes altogether. As we all know, there could be primary manufacturing processes as well as secondary manufacturing processes. There are also other manufacturing processes which are tertiary manufacturing processes like coating, new manufacturing processes like generative manufacturing or rapid prototyping, but we are restricting our classification to only primary manufacturing and secondary manufacturing. So, what is the need or purpose of primary manufacturing? The purpose of primary manufacturing is to impart basic shape and size to my material. It can be done in liquid state, it can be done in solid state, as well as it can be done in powder state. In liquid state, we all know the forming process. Any casting process, be it die casting or green mold casting, anything is a liquid state forming process. What are the solid state forming processes? Conventionally, what we know as the hot working or cold working processes, or all metalworking processes like forging, rolling, extrusions, they are solid state forming processes. Powder state forming processes are powder metallurgy, the way cutting tool inserts are produced. Okay. Next comes the secondary manufacturing processes. So, how the secondary manufacturing processes are different from the primary manufacturing processes? In primary manufacturing processes, we were giving or imparting basic shape and size. In the secondary manufacturing as well, we are doing the same thing, but there is a small difference. What is that small difference? We are imparting the final shape and size with tight control on dimension and shape. This cannot be achieved by casting or rolling, but this can very much be achieved by secondary manufacturing processes. Most of the secondary manufacturing processes are material removal processes. So, this is the basic classification of manufacturing processes. Now, let us go into the classification of secondary manufacturing processes. In today's course, manufacturing processes course, we are basically dealing with all secondary manufacturing processes. There are two major divisions. One is conventional manufacturing or machining processes and non-traditional machining processes. In other modules, non-conventional machining processes is being dealt with, and today we are starting with non-traditional machining process, module number 9. So, you all know by this time what are the conventional machining processes. They are like turning, milling, drilling, grinding, shaping. So, these are the conventional machining processes. And what are the some of the non-traditional manufacturing processes? One of them is abrasive jet machining, what we are going to cover today. Ultrasonic machining, which we would be covering in the next class. Another one is water jet and abrasive water jet machining. This would also be covered in this module. Electrochemical machining, electro discharge machining, laser beam machining. So, these 6 processes are the representative processes of non-traditional machining. There are other processes as well, like plasma machining, ion beam machining, electron beam machining. We are not going to cover all of them in this particular module. These 6 representative processes would be covered in details. Now, let us try to understand the characteristics of conventional machining process. So, first let us draw a turning. So, this is my blank, which is being turned. This is the chuck, this is my tailstock support, this is my tool. The job is getting given a rotation and the tool is given a feed, and this is the chip formation process which has been drawn here. This is my tool, this is my workpiece. So, this is my tool and this is my workpiece, this is my chip. So, here chip is being formed against the application of the cutting force. So, what are the characteristics? There is a macroscopic chip. In conventional machining processes, there is a macroscopic chip formation. How the chip formation takes place? It takes place due to shear deformation. These are the shear lines, as you can see. This is the shear plane, this is my shear angle. There is a requirement of the cutting tool, and the cutting tool needs to be harder than the workpiece. Material removal takes place because of application of the cutting force. The force is being imparted on the tool because of the cutting process, and the energy domain of conventional machining process is mechanical in nature. So, these are the 5 major characteristics of conventional machining processes. Now, let us see what are the characteristics of non-traditional machining processes. In non-traditional machining processes, material removal takes place quite often with chip formation, or even no chip formation may occur. Say for example, in abrasive jet machining process, what we are going to cover today, chip formation does take place, but the chips are microscopic in size, they are not macroscopic in size as in turning or milling. In another non-traditional machining process which would be covered later on, electrochemical machining, machining occurs due to electrochemical dissolution at atomic level. There is no microscopic chip formation even present. Next comes the question of physical tool. In conventional machining process, I require a physical tool and it has to be harder than the workpiece, but in non-traditional machining process, a physical tool may as well be totally absent. Say for example, in laser beam machining, we are machining with the thermal energy source of a laser beam. There is absolutely no physical tool available there. In water jet machining process, machining is carried out by high pressure water jet. So, it is a flexible tool, it is not a rigid physical tool. There is a water jet, but it is flexible. In electro discharge machining, however, there is a physical tool requirement. So, physical tool may be absent, it is not necessarily always absent, it may be absent. Similarly, in electrochemical machining as well, you require a physical tool. Now, other characteristics are, one of the major characteristics of conventional machining process was tool has to be harder. In non-traditional machining processes, tool need not be harder, it can be softer. Say for example, in electro discharge machining, one can machine very hard metallic alloys using copper as the tool material or graphite as the tool material. They are much more softer than the workpiece which are being machined like hardened steel or Inconel or titanium alloys. So, in case of electro discharge machining, tool need not be harder if a physical tool is present. Then comes the energy domain. Already we have identified in conventional machining, the energy domain is purely mechanical, where chip formation occurs due to shear deformation due to application of cutting force. But in non-traditional, it need not be necessarily mechanical, it can be other as well. There are different energy domains available for machining. For example, ultrasonic machining, abrasive jet machining, water jet machining, or even abrasive water jet machining, all these the energy domain is mechanical. However, in electrochemical machining, it is due to electrochemical dissolution. In electro discharge machining, it is a electrothermal machining process. So, we conclude that energy domain can be mechanical or it can be other energy sources as well. So, these are the major characteristics of non-traditional machining processes. Now, based on these characteristics, once again we can classify different non-traditional machining processes. What are they? Broadly, it can be classified as mechanical processes, where mechanical energy is used for material removal. We can classify it as electrochemical processes, we can classify it as electrothermal processes as well as chemical processes. For under chemical processes, what we have? We have chemical milling, photochemical milling. Photochemical milling is very much used in electronic industry. Under electrothermal processes, we have electro discharge machining, electron beam machining, laser beam machining. So, all these would be covered in the later classes. Now, let us come to the mechanical processes. Today, we are going to cover abrasive jet machining. This is a mechanical process where material removal occurs because of application of mechanical energy. Other processes are USM, WJM and abrasive water jet. Electrochemical machining processes are electrochemical machining, electrochemical grinding and electrojet drilling. So, this is the basic classification of non-traditional machining processes. Now, before we go into abrasive jet machining in a detailed manner, let us touch upon different non-traditional machining processes. This is ultrasonic machining. What is it? There is a tool in ultrasonic machining process. This is my tool. There is a workpiece. This one is my workpiece. And this tool vibrates with an ultrasonic frequency. What is the nature of vibration? Ultrasonic, the frequency of vibration is around 20 to 25 kilohertz and the amplitude of vibration is around 10 to 25 micron. When it vibrates between the tool and the workpiece, this area is supplied with abrasive slurry. As the tool vibrates, the abrasive particles interact with the workpiece. Most often brittle materials are machined. As these abrasive particles interacts with the workpiece, it basically induces controlled fracture in the workpiece and thereby material removal takes place. Now, let us come to another process which is electro discharge machining process. In electro discharge machining process, we have already learned what is the energy domain classification. It belongs to electrothermal processes. Here this is my tool, this is my workpiece. Between the tool and the workpiece, it is immersed in a dielectric medium, and a potential difference is applied between the tool and the workpiece. Between my tool and the workpiece, a potential difference is applied. As a potential difference is applied, the dielectric breaks down and there is a sparking. The thermal energy of the spark would melt some amount of material and gradually there would be material removal. So, this is about electro discharge machining. Now, let us come to electrochemical machining. Here material removal occurs because of electrochemical dissolution. Here also I have a tool and I have a workpiece, but it is not immersed in a dielectric medium, it is immersed in an electrolyte medium, and a potential difference is once again applied between the tool and the workpiece, and because of electrochemical dissolution, there is no sparking. Because of electrochemical dissolution, gradually the workpiece is removed or material is removed. So, energy domains are pretty different. Now, let us come to the need of non-traditional machining processes. Conventional machining processes were there, they were providing the economic benefits, manufacturability of different materials. However, gradually there was lot of development in the material side, lot of exotic materials were coming up, which could not be machined efficiently using conventional machining processes. So, thus this was one need, one requirement for which non-traditional machining processes were developed. Then there was innovative design and requirement, tighter tolerances and micro machining. So, these were the new requirements of the new age, which could not be met from the conventional machining route. So, a need or requirement was felt for development of non-traditional processes. Let us take some example. Say for example, you have to drill a blind hole, it is a square hole. Drilling a square hole using conventional methods is very difficult. Moreover, it is a blind hole having a dimension of 15 millimeter by 15 millimeter with a depth of 30 millimeter. Machining such a hole using conventional machining process is rather difficult. However, if one would like to machine it with electro discharge machining, it is a very easy solution. Now, let us come to the material point of view. There are new materials which are very difficult to machine. What are they? You have materials like inconel, it is a nickel superalloy, you have titanium alloys, you have carbide, ceramics. These materials are very difficult to machine, and all the time one cannot develop cutting tools for conventional machining which are much harder than the tool material. So, if they can be machined in a way where hardness does not come into picture, yes, they can be machined. In conel titanium, they can very easily be machined using electrochemical machining and electro discharge machining. Now, even within conventional machining process, there were some requirement like low stress grinding. Grinding is a finishing process, as we all know, under conventional machining process. When we grind, there may be induction or introduction of tensile residual stress. So, there is a requirement of low stress grinding. In conventional machining, if one has to do low stress grinding, then he has to reduce the productivity, which is not a very effective or efficient way of doing it. But electrochemical grinding can provide almost stress free surface. Then there are requirements of machining of composite, defold drilling and all of this. So, gradually the need for non-traditional machining processes were getting established in the industry, and nowadays they are very much there, and non-traditional machining processes are as essential as the conventional machining processes. One cannot fully replace the other one, but requirement or presence of both of them is very much required in machining industry. Now, let us come to abrasive jet machining, which is the second part of our lecture today. We are going to first study how abrasive jet machining, or what is the mechanism of material removal. What we have here here we have a nozzle. Okay. In this nozzle there is a opening or a inner diameter which is typically around 0.2 to 0.8 millimeter. Through this nozzle a mixture of gas and abrasive particles are fed. They are fed at a velocity of 150 to 300 meter per second. These abrasive particles, when they are issued from this particular nozzle, they would interact with my workpiece. Typically for abrasive jet machining, brittle workpiece, brittle materials are machined more efficiently. So if you are using abrasive jet machining as a machining process, you should rather try to machine glasses or other brittle materials rather than low carbon steel. Once these abrasive particles, these are my individual abrasive particles, when they interact with the workpiece, they have some amount of kinetic energy. As they interact with the workpiece, that kinetic energy is converted into mechanical work. They would indent the surface, they would create a small crater, and the kinetic energy would be absorbed by with the work done for producing this particular crater, and in this way with multiple impact gradually we will be getting a machining. So this is a pure mechanical domain process where the mechanical energy of a high speed abrasive is used for machining the material, and the machining occurs because of the brittle fracture of the workpiece. Now let us come to the general description of abrasive jet machining equipment, what we require. This is the first requirement, which is my compressor, because I require a gas. This compressor is fed through the line through a valve. This is typically a quarter turn valve. Then you have this piece of equipment. What is this? This is a air filter. Whatever air is coming out of the compressor, oil and moisture is removed. This is a dryer. This is a moisture separator or a dryer. This can be a regenerative dryer or it can be other kind of dryer as well. Here you have a pressure regulator. Say for example, your compressor is issuing air at 12 bar and your working pressure is 5 bar. So this pressure regulator would be reducing or giving you a regulated supply. After the pressure regulator, it goes into this particular chamber. This chamber is known as the mixing chamber. Within the mixing chamber, abrasive is fed from the top through a hopper, and this is a electromechanical shaker. So with this, the mixing chamber is always being violently vibrated, so that there is proper mixing of this air or the carrier gas and the abrasive particles. Once they have mixed together, then they are fed through a line like this, and here you have a pneumatic electro-pneumatic valve, on-off type valve. This is not a quarter turn valve, this is on-off type valve. So when the valve is on, the abrasive and the gas mixture is allowed to issue from the nozzle, which we have already discussed in the previous slide. It is allowed to issue from the nozzle, which has been shown here. This is your workpiece, and this is the table with a lead screw, so that the workpiece can be moved below the nozzle, and the whole thing is there in an enclosed chamber, because as the abrasive particles interacts with your workpiece, they will generate lot of dust. So it has to be properly taken care of. It cannot be simply taken out in the atmosphere. There has to be proper exhaust system, so that the abrasive and the material which is being removed can be separated properly before releasing the air in the atmosphere. Now let us come to the process variables which affect my abrasive jet machining process. What are the process? What could be the process variables? I require abrasive, so I need to classify what are the, how this would definitely be a major process variable. What would be the material of the abrasive? Generally aluminum oxide and silicon carbide is used. Quite often glass beads are also used. Then comes the shape of the abrasive. Once you have decided that you are going to use aluminum oxide or silicon carbide, typically their shape is irregular, but they are rather sharp. If someone is interested in using glass beads, their shape would be typically spherical. Now, once we have decided about the material and the shape, then comes what would be the size. Size of these abrasive particles are rather less, they are in the range of 10 to 50 micron. Then how much abrasive particle should I use? That is the mass flow rate. Typically the mass flow rate of abrasive particles are around 2 to 20 grams per minute. So, they are also consumption rate of abrasive is rather less. Now, as we have discussed earlier, we require a gas to propel those abrasive particles. So, other than these abrasive particles, this carrier gas would also play an important role. Generally, air can be used, or else carbon dioxide or nitrogen can be used. Then we do not require, if you are using carbon dioxide or nitrogen, then you do not require this compressor. Instead of that, you will issue the gas from a gas cylinder. So, instead of the compressor, you will issue it from the gas cylinder, that is also possible. So, as a carrier gas, typically air, carbon dioxide and nitrogen is used. Typical density of the air is something around this. Velocity is around of the gas is around 500 to 700 meter per second, pressure is around 2 to 10 bar, flow rate is around 3 to 5 to 30 LPM. One of the most important parameter is the pressure of this carrier gas, because depending on the pressure we will be getting a particular velocity, and that will decide to what extent my abrasive particles should be, or the abrasive jet would be, abrasive particles would be accelerated. So, once abrasive and the carrier gas they have mixed together, we will get the abrasive jet. How do I classify or identify the parameters of the abrasive jet? One is once again the velocity. The velocity is around 100 to 300 meter per second. If you go back one slide, you can see velocity of the carrier gas is 500 to 700, but this is 100 to 300. Why this drop? Because once the abrasive particles are mixing with the carrier gas would lose momentum, and it will gradually transfer its momentum to the abrasive jet, so that the abrasives can be accelerated, and in the process your velocity will drop down. Then there is mixing ratio. What is mixing ratio? How much abrasive you are pumping into the system as compared to the mass flow rate of the gas. If you are pumping too much abrasive, they would not be accelerated properly. So, mixing ratio is once again a very important parameter. Then standoff distance. How far is your nozzle from the jet, from the workpiece? This is your workpiece, this is the end of the nozzle. So, this is your standoff distance. Typical standoff distance is around in millimeters. Then comes the impingement angle, at what angle the jet is interacting with the workpiece. If there is no technical or geometrical requirement, typically impingement angle is around 90 degree, but it can also be as less as 60 degree. Then comes the nozzle material, because this nozzle material has to be such, it is handling abrasive particles which are moving through the nozzle at 300 meter per second. So, we need to understand the requirement, and the requirement is it has to be wear resistant. Typically tungsten carbide nozzles are used, or even wear resistant sapphire nozzles are used. The inner nozzles are characterized by their internal diameter, and the internal diameter of the nozzle would be 0.2 to 0.8 millimeter. Why they are to be like wear resistance? If they are not wear resistant, then you will not get good life from the nozzle. Quite often under industrial situation, the life expected is around 100 hours or 10 hours. If you are getting 10 minutes by using steel nozzles, then all the time you would be changing your nozzle, there would be no production. So, appreciable life of the nozzle is very important, for which we require a wear resistant nozzle material. Now, let us go into gradually the modeling of material removal in abrasive jet machining process. Today we are going to model only for brittle materials, and it would be considered as those abrasive particles interact with the workpiece, The material removal occurs due to brittle fracture. There is another consideration. Once a single abrasive particle interacts with the brittle material, there would be a fracture, and this fracture would be assumed to be hemispherical, and the diameter of the fracture would be the caudal length of the indentation. As the abrasive particle interacts with the workpiece, it will create a small crater. That crater would be created because abrasive particles are highly kinetic energetic. So, the kinetic energy of the abrasive particle would be absorbed as it creates that crater, and the diameter of that particular crater or indentation would be equal to the caudal length. Another assumption is kinetic energy of the abrasive particles would be considered to be fully utilized. It is not partial. Whatever is the kinetic energy, we will assume that total kinetic energy is utilized in doing the work done. Further, abrasive particles would be assumed to be rigid, they would be assumed not to disintegrate, and they would be spherical in shape, and their particle size would be characterized by the mean diameter. Now, let us come to the modeling part of it, modeling of material removal rate in abrasive jet particle. We were always saying one abrasive particle. So, this is one small abrasive particle. Abrasive particles are not completely spherical, there is small undulations, however, we are assuming it to be spherical. What else we are assuming? We are also assuming when it interacts with my material, it creates a hemispherical fracture, and that hemispherical fracture is identified, or indentation is identified by this caudal diameter, caudal distance 2r. Okay. Now, we need to find out how much is this value of this r. How we can find it out? Let us look into the equations. First, it says AB square, this particular distance hypotenuse is equal to AC square plus BC square. By rearranging, I can write BC square, which is nothing but the small r, is AB square minus AC square. AB is nothing but the radius of the grid, and AC is nothing but the radius of the grid minus delta. What is that delta? That delta is the indentation. So, assuming this delta to be very, very less, it would be very less, I can get an expression of the radius of my indentation, which is root over grain diameter or grid diameter into indentation. This particular relation would be very useful in finding out the material removal rate. Once I have this r, I can also find out how much is the amount of material removal in a single impact. How much is my material removal? Single impact material removal is this hemisphere. So, what is the volume of my hemisphere? Volume of my hemisphere is 2/3 pi r cube, where r is nothing but the radius of that indentation. Already we had an expression for r, so I can put that expression here to get a expression for amount of volume of material removal in a single impact. Now, let us try to see what is the kinetic energy of a grain or a particular abrasive particle. Kinetic energy of a particular abrasive particles is half mv square. M is nothing but its volume into its density. So, this is my final expression of my kinetic energy. Now, where is this kinetic energy expended? This kinetic energy is expended in doing the amount of work. So, I need to write down equations or derive equations for finding out how much work is being done. When it is indenting the abrasive particles, when it is gradually going inside the workpiece, initially my force is 0 and this force is increasing to a value of F. How can I estimate this F? This F is indentation area into hardness of the workpiece, that is a good estimation. So, work done is half F into delta. Why is it half F into delta? Because F was varying from 0 to F, it was not constant all the time. So, now I have a relation for the total work done for doing an indentation, which is half F into delta, which is nothing but half phi r square into H, H is the hardness into delta. So, we have two terms, one is the work done, another one is that of the kinetic energy, and we were saying the total kinetic energy is converted. So, we can equate them to get some more expressions. So, we are equating the total work to the kinetic energy. There is an assumption, the assumption is the whole of kinetic energy is converted, and then once we equate it, we can find out the value of delta, which is the indentation depth, and this is the final expression for delta, and delta seems to vary with dg. As you increase dg, you would have more indentation. It seems to vary with velocity. If your particles are much more energetic, definitely your indentation would be higher. If the hardness of the work material is more, the indentation would definitely be less. So this particular expression looks physically verifiable. Now let us come to the material removal rate. How much would be my material removal rate? Material removal rate would be amount of material removed, this gamma b, in a single impact into number of impacts. So that is what we have written, amount of material removed in a single impact into number of impacts. So it is very simple. How can I estimate number of impacts? Number of impacts can be very easily estimated if I know what is my mass flow rate of the abrasive divided by mass of a single grit. So mass flow rate of the abrasive would be set on the machine, and this is mass of a single grit. So once again one can get material removal rate in case of a brittle material as this particular expression, which is written here in a better manner. So this was the expression. In that, delta, the indentation depth, is still unknown. So we have already determined the value of the indentation depth. So now we are going to put that in this particular equation to modify the material removal rate expression, and the modified material. So this delta is being replaced with this expression, and we get a modified material removal rate expression of this. How is it related? If we increase abrasive flow rate, material removal rate is expected to increase. If we increase the velocity, the kinetic energy is increasing, so material removal rate is expected to increase. If you are using harder material, harder work material, definitely it would be much difficult to machine, so material removal rate would go down. Now let us, we have already identified all the process parameters. We have identified one of the major material machining characteristics, which is material removal rate. We have also modeled, just now we have modeled the material removal rate as well. Now let us see the effect of process parameters on material removal rate. This is my modeled information, and these are actual experimental observations. So what we see here, we see as we increase abrasive flow rate, material removal rate increases. This is a good observation, and it matches with my modeled value, but there is a deviation. What is that deviation? After a particular material abrasive flow rate, there is a reduction. Why is this reduction? That can be explained very easily from this particular graph. How can we explain this one? This is mixing ratio. What is mixing ratio? Mixing ratio is the ratio of abrasive flow rate divided by gas flow rate. As we go on increasing the mixing ratio, we are putting in more abrasive particles, so definitely material removal rate is going on. But beyond a particular point, there are so many abrasive particles, gas does not have enough momentum to accelerate them. So no longer there is benefit, there is a reduction in material removal rate. A similar model would be done under abrasive jet machining process, that is another abrasive water jet machining process. A similar modeling would be done. So at that moment of time, it would be very clear to you why this phenomena occurs. Now let us try to see the effect of gas pressure. Let us try to see the effect of gas pressure on material removal rate. Once again, this is my modeled equation, which says if you increase velocity, your material removal rate is going to increase as well. How do I increase velocity? With increasing gas pressure, this velocity is going to increase, so the material removal rate is also going to increase. As you increase the gas flow rate, you can pump in more abrasives, so you have different graphs. As the gas flow rate increasing, for a constant mixing ratio, your material removal rate you get is more. This is material removal rate by abrasive flow rate. This is a constant straight line. There is a catch. What is the catch? When I am increasing the abrasive flow rate, I am also increasing the gas flow rate, so that I get a constant mixing process. So, whatever equation we have developed here, it is very true, whatever equation we have developed here, it is very true provided my mixing ratio is constant. If mixing ratio is constant, material removal rate changes with abrasive flow rate linearly as we have modeled. Now, let us come to the effect of process parameters on material removal rate. This is another effect, which is the standoff distance. The model that we have developed, in that there is no effect of standoff distance, but it is there in a implied form. What is that implied form? This is my nozzle, this small piece is my nozzle, and it is issuing the jet. As the jet is being issued, this jet is interacting with the air molecules around it. It is a submerged jet, it is a air jet within the air. So, it will entrap air from the atmosphere, and as it entraps air, there would be flaring of the jet. The jet would be very straight as it is being issued, but after a length typically around 10 internal diameter of the nozzle, it will start flaring out. So, if your workpiece is very near to the nozzle, you get a shape like this, where the material removal is not much, because the after interaction they cannot remove. If they are within appreciable distance, material removal rate is very high. Till C, more or less it is constant, then once again it droops down, because as it flares out, the energy of the particle is lost as it interacts with the air molecules present in the atmosphere. So, this though has not been included in our model, but it is very much there in an implied form. Now, let us come to the applications of abrasive jet machining process. Already we have said that in abrasive jet machining, material is removed due to interaction of the high velocity abrasive particles with the material, and as it interacts, it creates small indentation or craters, and those craters are formed because of the brittle fracture of the material. So, typically brittle materials are machined using abrasive jet machining, and they are machined for drilling holes of intricate shapes, and as because it is brittle material, quite often those materials are also hard. In abrasive jet machining, there is not much of cutting force, thus it can also be used for machining fragile objects, heat sensitive materials, because there is no thermal damage or very less thermal damage, and as well as brittle materials. AGM can be used in different modes. It can be used for drilling operation, it can be used for deburring operation, it can be used for etching operation, it can also be used for cutting or slitting operation, and there is another interesting application, which is mechanical etching. Abrasive jet machining is not only finding application in conventional, in non-traditional machining of large dimensions, they are also finding application in micro machining of brittle objects. However, any process would have its advantages and some limitations. So, let us look into the limitations of abrasive jet machining process. Material removal rate in abrasive jet machining process is rather low. In conventional machining process or other non-traditional machining process, material removal rate can be very high, but here material removal rate is around 15 millimeter cube per minute, so which is not much. There is another problem. Abrasive particles quite often gets embedded in your workpiece. If they get embedded in your workpiece, it is contamination of the workpiece. So, in certain applications you cannot use them. In any jet manufacturing process, be it abrasive jet, abrasive water jet or even laser beam machining, there would be some amount of tapering due to flaring of the jet. As the jet flares out, it would lose energy and there would be tapering. And as we have said earlier, environmental problem is a problem in abrasive jet machining. In abrasive jet machining, it has to be done in an enclosed environment, and after machining lot of dust would be generated, so they cannot be simply thrown out. So, in abrasive jet machining process, there is lot of load on the environment and which has to be taken care of, otherwise we would be polluting the environment unnecessarily. Now, let us come to the quiz part of it. There are 4 questions under quiz, and this basically tries to give you a flair of the subject what you have learned today. Abrasive jet nozzles are made of low carbon steel. Is it made of HSS? Is it made of tungsten carbide or stainless steel? The answer is tungsten carbide, but knowing the answer is not enough. You need to know why it is correct. We all know in abrasive jet machining, nozzles are handling high velocity abrasives. What are those abrasives? The abrasives are aluminum oxide, Al2O3, silicon carbide. They are abrasive particles. What is their velocity? Their velocity is around 300 meter per second. So, the velocity is rather high. At such a high velocity, when these abrasive particles are moving through the nozzle, if the nozzle is not wear resistant, it is going to give you a very poor quality tool life. That means it will wear out so fast, you have to change the nozzle quite often. So, you should use a very wear resistant material for building the nozzle. Out of the listed materials here, tungsten carbide is the most wear resistant material. Low carbon steel, even HSS cannot provide such amount of wear resistance. So, this is your proper answer. Now, let us go to the next question. Material removal rate in abrasive jet machining of glass is around 0.1 millimeter cube per minute, 15 millimeter cube per minute, 15 millimeter cube per second, or 15,000 millimeter cube per minute. Basically, here there is a change of order of at least 6 times. This option and this option there is a change of order of 2, because this is almost 100 times less. Here also it is multiplied by 60. Here also there is a change of order of 100 from this place. So, which one is correct? We all know one of the major limitation, if you go back, limitation of abrasive jet machining is material removal rate is rather low, but it is also not as low as this. So, the appropriate answer is 15 millimeter cube per minute. Now, let us go to the second quiz, second page. Material removal takes place in abrasive jet machining due to electrochemical action, mechanical impact, fatigue failure, or sparking on impact. Which one is correct? We all know that abrasive jet machining is a mechanical domain non-traditional machining process. We also know material removal occurs as high energy particles interact with the workpiece, and in the process the kinetic energy of the particle is converted to the work done in producing an indentation or crater. Thus, it is not because of electrochemical action, it is not because of material fatigue, neither it is because of thermal action or sparking on impact. So, what is the correct answer? It is the mechanical impact. That is the major contributor for material removal in abrasive jet machining. The last question. As the standoff distance increases beyond 5 millimeter, depth of penetration in abrasive jet machining increases, decreases, does not change, or initially increases and then remains steady. We all know that the jet diameter is typically submillimetric. It is around 0.5 to 1 millimeter. That jet is issued from the nozzle, and that jet interacts with the air around us and it flares out. As it flares out, it remains more or less straight over a distance of 5 to 10 d. Beyond that, it does not remain constant. That means, if you are thinking of a jet diameter of 1 millimeter, it starts to flare out possibly from 5 to 10 millimeter onwards. Thus, if you go on increasing the standoff distance beyond a particular value, there would be reduction in the depth of penetration. So, this is my correct answer, not the other ones. Now, let us go to more complicated problems or solve problems. Here, you have to estimate the material removal rate in AJM, in abrasive jet machining process, where it is a brittle material with a flow strength of 4 gigapascal. Abrasive flow rate has been given, velocity of the abrasive is given and density of the abrasive is also given. Already we have developed a model, this is my model. So, from this model once I put, so 2 into 10 to the power minus 3 by 60, that is the mass flow rate of the abrasive, 200 is the velocity of the abrasive, 3000 is the density, and 4 into 10 to the power minus 9 is the flow strength of the abrasive. The second problem, material removal rate is given, calculate material removal per impact. This is another very good indicator. If mass flow rate of the abrasive is given, density is given and the size of the abrasives are given, as well as you have to find out the indentation radius. How do I do it? First I will estimate how much is the mass of the grid. I can estimate by this. Once I know the mass of the grid, the mass flow rate is given, I can find out what is the number of impacts per unit time. This is my mass flow rate, this is my mass of a single grid. So, these many impacts are occurring per unit time. Then I will find out how much is the total volume removed in a single impact, because I know material removal rate, I know number of impacts, thus I can find out what is the amount of material removal in a single impact. Once that has been done, we have already assumed the crater is hemispherical in nature. So, I know how much is the volume and I can equate that to this particular volume of 1960 micron cube. So, indentation radius we are getting around 10 micron. So, through these two problems there are two things to learn. We are getting a typical indentation radius which is around 10 micron, and we also got a typical MRR which is around 48 millimeter cube per minute. So, it is in tens of millimeter cube per minute, not in hundreds, neither it is 0.1. So, these two solved problems not only are giving you exposure to this, but also giving typical industrial values. Now, to conclude, let us come to the summary of today's lecture. What we have learned today? We have learned about the characteristics of conventional as well as non-traditional machining processes, and once we have identified them, we can also differentiate between them. Another very important thing we have learned, that is the classification of non-traditional machining process. There are different types of non-traditional machining process. Today we have discussed abrasive jet machining, which is a mechanical process. Then why there should be non-traditional machining process? Conventional machining process was doing it fine. So, there was some non-traditional, that has also been explained. As far as AJM is concerned, we have identified the process parameter, equipment models. We have also discussed how to model material removal rate. We have studied the effect of process parameters on material removal rate, and as well as we have indicated the application areas and limitations of abrasive jet machining. So, with that I conclude. Thank you so much. Class on NPTEL sponsored manufacturing process 2. Today we are going to discuss ultrasonic machining, which belongs to the module number 9 on non-traditional manufacturing. We have started module number 9 with abrasive jet machining. So, today is our second class. So, lecture number today is 9.2. I am Soumitra Pal of Department of Mechanical Engineering, IIT Kharagpur. Before starting with the lecture, let us go to the instructional objectives. Once you go through this particular lecture, you would be able to describe the basic mechanism of material removal in USM. What is USM? USM is ultrasonic machining. You would be able to identify process parameters of ultrasonic machining. In any machining process, machining characteristics is very, very important. So, once you go through this lecture, you will be able to identify the machining characteristics of ultrasonic machining. Describing something or identifying something is good, but you would also be able to analyze the effect of different process parameter on one of the most important machining characteristics, which is material removal rate or MRR. Once you have done that, you would be able to draw variation in MRR, that is whatever is the variation in material removal rate when someone is changing different process parameters. Other than that, you would be able to develop mathematical models relating material removal rate with different USM process parameters. Understanding the basic effect of process parameter from experimental data is one thing, and developing full mathematical model gives you much more better insight into the process. Any non-traditional machining process, or for that matter conventional machining process, requires equipments. So, for ultrasonic machining there is ultrasonic equipment. So, once you go through this lecture, you will be able to identify the major components of ultrasonic machining equipment and state working principle of those modules or sub modules. You would be able to schematically draw the ultrasonic equipment, and like any other non-traditional process that we are covering in this module, you would be able to list at least 3 applications and at least 3 limitations of USM. Now, let us go into the classification of non-traditional manufacturing process. Earlier in my first lecture on introduction and abrasive jet machining, we have already gone through the classification. So, once again we will briefly touch upon the classification of non-traditional machining processes. You have mechanical processes, you have electrochemical processes, you have electrothermal processes and chemical processes. So, these are the broad areas. Within mechanical processes, we have already discussed about abrasive jet processes. Today, we are going to discuss about ultrasonic machining processes. Later on, we will be discussing about water jet and abrasive water jet machining processes. In electrochemical machining, we will be discussing about ECM. In electrothermal processes, we will be discussing about electro discharge machining, EBM as well as laser machining. But today, we would be concentrating only on ultrasonic machining processes. So, let us come to the process description of ultrasonic machining. Like any other machining process, any other non-traditional machining process, you are interested in machining a workpiece. So, this one is my machining, this is my workpiece, and there has to be a tool with which I am going to machine it. This is my tool. This tool vibrates over the workpiece. With what kind of vibration? That vibration is around 19 to 25 kilohertz.